Hi, I've never done a YouTube channel or like YouTube videos before, but I just wanted to do one of my favorite proofs of all is the Euler's formula proof. This might look really scary, but I swear to God, I'm gonna explain this really like easy. Like it's at a beginner level, okay? All you need to know for this is basic trigonometry, like SOHCAHTOA, and just some basic like calculus, but it's okay. I'll show you like what you just need to know, okay? So just basic trigonometry, that's all. Okay? So I say that this part is easier to understand, or at least to prove geometrically, than this. So we're gonna start with the trigonometric functions cos theta plus I sine theta. Let's just not think about the I for now, and let's just think about cos theta and sine theta, what this is telling us. So just hear me out. Consider a circle, a unit circle. So it has the radius of 1, right? So then this, 1. Okay? Now, if I were to draw from center to circumference, any line, right? Center to circumference, that will be 1, right? This line, it's a radius, 1. You bring that line down from the circumference, that creates a right angle triangle with the hypotenuse 1, right? And then SOHCAHTOA dictates that this be equal to cos theta then, because usually it's cos theta equals to adjacent over hypotenuse. So hypotenuse times that out, and it'll give you the adjacent, aka this line, and then sine, same story, you times the sine theta by the hypotenuse, and it gives you the opposite, right? This line. This would be sine theta. Now, you might be thinking, what the hell does this have to do with anything? What does this have to do? Well, let me tell you a little bit something about imaginary numbers, the complex plane. Oh, that's what it was. I was doing outtakes of this. I was calling it like the imaginary dimension. Okay. Just remember that, okay? Just remember that. A triangle, right angle triangle inside of a unit circle. Okay? What you might have been taught in school is a number line, right? Let's go -2 to 2 over here, right? This goes, yeah, that's pretty good. Okay. This is a number line from -2 to 2, okay? And then, that's not all though. There's actually another thing, like in a graph, you know, like x and y. You have your x over here, -2 to 2. You actually have a y too on the number line. They just didn't tell you about it because they're liars. You have a line that goes right down 0, and it's called the complex plane. The units for it is I. So you got I, and 2i, so on, it goes up. And you got minus I, and then the 2 minus I, yeah. And then it looks like this, right? Just like a normal graph. I know this looks scary, but just hear me out, okay? And then with this plane, right? The only way you can access this plane is through imaginary numbers and complex numbers. I know complex numbers, scary name. Why the hell did they call it like complex? Well, imaginary numbers is when it just consists and just goes up here, right? Or down. It just follows that y-axis. But complex numbers, on the other hand, they have both a real number, like 1 and 2, or -1 and -2, plus an imaginary number. So it will be like a plus bi. That's what a complex number looks like. This b though, this bi, this is what we're going to concentrate on. Okay? All the imaginary number does, in reality, is rotate something 90 degrees, like on the complex plane. Okay? I know that sounds stupid. It sounds really stupid, okay? But just hear me out. If you had something like 1, right? then you times it by I. Then you go from 1 to I. You times it by I again, I squared. Oh yeah, I forgot to mention, I is dictated by, it's called the square root of -1. That is I's identity, okay? Square root of -1. So you square that, right? You square I, you get -1. 1 times -1, you go to -1, right? You cube it, that goes to -I. Okay, I know this is done. And then you times it by, I to the power 4, you go back to 1. I know this is not a very nice circle, but it's a circle to me, okay? It's a circle to me. All it does is rotate a number, okay? All it does is that rotation. But then, orange. How do you know, like, how much it rotates? How do you know my... Oh my god, I'm so sorry. My brain's all fuzzy today. Okay, let me draw an up-close version of this circle for us. Oh, that is an ugly circle. Okay, let me just fix that up. Okay, so now that we have that number, right? Now we have that circle. Good. I up here, 1 down here, -1 here, and I here. Oh, wait a second, this looks similar. It's our unit circle from before. From the center, there, the radius is 1. So that means if we wanted to find any point that, because if you times it by I, right, it only moves in this circle. That is the motion, right? The cycle of timesing something by I. It rotates 90 degrees each time. So if you wanted to find something that is moving on here, right? You want to find the coordinates? This is basically what it is, right? It's kind of like how polar coordinates work. So we bring that coordinate, kind of make like a line here to the center, right? We got the hypotenuse 1 since it's on a unit circle, right? It's in a unit circle, so this hypotenuse is equal to 1. When you bring the line down, hey, look, it's our buddy from before. So then cos theta, and this is sine theta. But wait a second. Where the hell does the I sine theta comes from? Well, you see, since it's on the imaginary plane, right? If we don't times it by I, all this will do is bring this line down here. It'll just get added to the real number line, right? So it'll just be cos theta plus sine theta on the real number line. So you have to times it by I to get, like, it goes up the y-axis, you know? And that is the cos theta plus I sine theta. Oh, I forgot to mention, I think the standard for this is that you have to have the degrees in radians. I don't know why I didn't mention that earlier, but yeah. So now we're getting onto the part with the scary, like the Euler's number, right? E theta I or I theta, whatever. So this, you need to know a little bit of differentiation or however you say it for this, but it's okay. I'll cut to the chase, right? Consider the function e to the x. When you differentiate this, right, dy over dx, you differentiate this, you get e to the x again, okay? Just bear with me. That's just the way it works. We could do a proof on it maybe some other time, but just accept it. It's the way it is. Differential of e to the x is e to the x. When you have e to the 2x, right, we use something called the chain rule. I'm not going to show you the exact, I'm not going to write out the rule for you in the, like, notation, because I think, like, some of the beginners might have a heart attack. So, look, okay? You have e to the 2x, right? dy dx here. Okay, you got this? So you bring this 2x down, right? Okay, you have to differentiate this. using the power rule. N, x, n minus 1. Okay? So you differentiate this. X is to the power 1, right? So you get rid of the x since it's going to be 1 minus 1, 0, and everything to the power 0 is equal to 1. So you get rid of the x. No more x. And then this is a constant, right? Oh, no, sorry, I'm getting a little confused. So then it's just 1 times 2. So the differential of 2x is 2. So you bring this differential down over here, okay? You bring it to the front. You got 2e. Once you bring this differential down, you don't change anything else. That's all, okay? It's still 2x. So if you can see this, this is how it is. Now you might be wondering, like, oh, why you waste my time with this? This is like stupid. I don't see how this works. Okay, now just hear me out. Just hear me out. Okay? E to the theta. No. Okay, let's keep this as x. I don't want to change the signs. So let's just have an x. E to the x I dy dx. Now, from what I showed you earlier, you can probably guess it's I, E, X, I. We're timesing this. So this is, okay. One thing about differentials. They show the rate of change of a function or a graph, right? So what this tells us is that this has the rate of change of I, right? It's getting times by I each time. So, from what I told you earlier, when you times things by I, what it does is it rotates it. What does that give us again? It's just 1 minus 1, I minus I. What does it do again? Rotates it. It's the worst circle ever, but that function is showing a centripetal motion, right? But the graph is doing this, right? Therefore, now you might be wondering, like, what does this have to do with it? What does this have to do with it, right? This shows that since it's moving in this, right? If you want to know the point at, like, where it is at any point, then it's on this circle, right? It's on this circle. Sorry, I got a little angry, guys. Remember this from earlier? Yep. Cos theta, sine theta. Proved. I'm sorry if my proof for the differential was kind of bad. I'm still like, I don't really, yeah. But I'm pretty I hope you understood the part with the trigonometric functions. So, yeah, that was my first video. Thank you. Bye.